Hello and welcome to Chapter 6.5 from Stevens' Introduction to Statistics, the Think and Do book. In this chapter, we are going to look at something called the normal approximation to the binomial distribution. And this approximation is actually not necessary if you have software or even a pretty good graphing calculator. But if you're a table user, we really do need this approximation. So we'll go over it for the practicality of us table users. Okay, so the idea is that back in chapter 5.3, we use the mean and standard deviation of a binomial probability distribution where the mean was equal to n times p and the standard deviation was the square root of n times p times q. And we use that to calculate z-scores of x minus mu over sigma. And basically we said, alright, if we have a z-score greater than 2 or less than negative 2, then x is unusual. Alright? And this was helpful because getting the exact probabilities of more than or less than a particular value is difficult for us table users when n was large, right? So my binomial probability tables in the back of the book only go up to 20. So if you have a large number, it's hard to get those exact probabilities and use the 5% rule for something being unusual. So basically we sort of cheated and we said, all right, we'll calculate the z-score. But now that we have a normal distribution, we can actually get the exact probabilities. But that's for a continuous random variable, and in this case we're dealing with a discrete random variable. And here's an example of how this applies. Right, suppose you are a hospital administrator and you're looking to highlight your hospital's noteworthy achievements. One of them is the survival rate for a certain type of cancer. And what you notice is the national 5-year survival rate for a certain type of cancer is 64%. So that's the national 5-year survival rate. You have seen 34 cases in your hospital, and 24 of them have survived over the 5-year mark. So you have a 5-year survival rate of 71%. About 71. So notice your survival rate is much higher than the national average. It's 7 percentage points higher. And the idea is we want to determine whether or not this is noteworthy. Is this a big deal? Is it, maybe it's just a random variation and you happen to get lucky. But it's hard to tell. 7%, is that a significant difference or not? So what we're going to do is we're going to say, all right, if the true survival rate is indeed 64%, what is the probability of getting 24 or more survivors in the 34 cases we saw at this hospital? Right? If that probability is really small, then we could say, yeah, we're doing something special at this hospital. If that probability is not small, then it might just be random fluctuation. So here's the idea. So here again we have 34 as our sample size, and we don't have a table for that, but we'll use the normal approximation to the binomial distribution. Okay, so here's the idea behind this approximation. When n times p and n times q, that's the sample size and the probability of a single success, sample size, probability of a single failure. When those products are both bigger than 5, the binomial probability distribution looks a lot like the normal distribution. And specifically the normal distribution with mean mu equals n times p, standard deviation, square root of n times p times q. Because that's the mean, I erased that. That's the mean and standard deviation for the binomial probability distribution. And this graph sort of shows you what we mean here. If you look at the binomial distribution, that's the bars here, all the various bars, and those are the probabilities for each discrete value, right? So these are discrete values of survivors, really, in this case, out of 36, right? So the probability of getting 20 survivors out of 36 patients is right up here at about 0.11 maybe. And so on. But if you actually look at the normal distribution, with mean equal n times p and standard deviation equal the square root of n times p times q. That's this curve. What you'll notice is the curve does a pretty good job of matching the discrete distribution. And so that's what we're going to do. We're going to use that normal curve to approximate probabilities from the binomial distribution. So here's the process. And again, look what we're trying to do in this example. We're trying to say, what is the probability of getting 24 or more survivors in 34 cases? Right. So here's the idea. If we want to find the probability that x is less than or equal to some given value, x star, or the probability that x is greater than or equal to some given value, x star. In this case, in our example above, x star was equal to, was it 24 survivors? Right? Was it 24? Yeah, you got 24 survivors out of 34 cases. Then here's what we do. We get our mean for the normal distribution is n times p, and the standard deviation is the square root of n times p times q. And then we convert that x star, say 24, to a z-score with the standard formula. It's the x value minus the mean over the standard deviation. And then the probability that I get x from my discrete distribution less than or equal to some value is approximately equal to the probability of getting a z from my continuous distribution less than the corresponding z-score. Right. And the same thing goes with greater than. And then what we want to do is make a conclusion about the likelihood of this thing occurring by chance. And we'll stick with the convention that if I have x, if the probability of getting an x value less than or equal to what I have is small, specifically smaller than 0.05 or 5%, or the probability that x is greater than or equal to some high level is smaller than 0.05, right? This is the 5%. Right? If those probabilities are less than, if one of those probabilities is less than 5%, then we will call x star unusually large, unusually small, or unusually large, right? And we were able to play that game back in chapter 5, but your sizes, your population sizes n was only 15 or 20, 1 to 10, 15 or 20, because that's all we had in the tables. So now we can play that game for any sample size, because we can approximate it with the normal distribution. By the way, most texts would say you have to take that x star and you either add 0.5 if you're doing an inequality one direction, or you take the x star and subtract 0.5 if you're doing an inequality in the next direction. But that tends to confuse more people than it helps, and the accuracy that is gained, it's still an approximation, so it might be a better approximation. But it's a lot of work, and students tend to add 0.5 when they should subtract, and vice versa. So we're just going to not worry about the continuity correction and just use the actual value. Okay, so let's go back to our preliminary example, right, where the hospital administration, the national survival rate is 64%. You saw 34 cases. That's going to be n. And in your hospital, 24 of them survived. And that's 71%. So you have good reason to believe that you're doing something really good here, because 71% is greater than 64%. Should this be considered a noteworthy achievement, or could this merely be a result of random variation? So here's what we want to do. I'm going to start from the graph. Here's our x, right? That's our discrete variable, number of survivors out of 36. And you want to find what's the probability of getting 24 or more survivors, right? You want this probability. If that probability is really small, you're doing something special. If it's not that small, it might just be, random variation. So what we do, let me erase these, we convert x star to a z-score. But we are going to assume that the probability of success for any single person is 0.64. So we'll assume the national rate of 64% is correct. And by the way, that if p equals 0.64, Q is going to be what? 0.36, right? Remember, these two things always add up to 1. All right, so the mean is n times p, so the mean is 21.8. So of the 34 cases you saw, you would expect 21.8 if that 64% thing is correct. And you got 24, so you're certainly more than you expected. The standard deviation is the square root of n times p times q, which is 2.8. So now I convert my x star of 24 to a z star using this formula. X star minus mu over sigma. So it's 24 minus 21.8 over 2.8 is 0.79. So this z star right here is actually 0.79. And right away you can say, well, that's not that extreme. A z-score 0.79, usually when we start talking unusual, it has to be around 2, correct? So the probability that I get greater than or equal to 24 survivors out of 36 is equal to the probability, actually it's not equal, it's approximated by the probability that z is greater than 0.79. And again, the z table doesn't give areas to the right, it gives areas to the left. So, the z table will give the value here. I want this value here, so I have to subtract the value I get from the z table from 1. So it's 1 minus the probability that z is less than 0.79. So let's go to the z table here. Oh, you know what? I'm going to open this up to full screen. I've been missing that. Okay. So I'm going to go to the z table and look up 0.79. Z table. It is a positive z-score, so I have to go to the positive z-table score. Z table. I'm looking for 0.79, right? 7 go across, 0.7852. I'm going to take that number back to the page. 0.7852. So 1 minus that, 0.2148, or about 21.5%. So what that says is that even if the 64% survival rate, the national survival rate, is accurate, then in random samples of 34, the number that you saw, you can certainly expect about 21.5% to have a value of 24 or greater. So while your 24 is certainly above average, or above what you would expect, you'd expect, even just due to random variation, to get 21.5% at that level or higher. So it's good, but it's not really a big deal. Specifically, when we start talking about significance, it won't really be considered significant. Okay, so let's take it to another. So here we had a difference. By the way, I want to go back and look at this difference. This difference, the national survival rate was 64%, right? And the hospital survival rate was 71%. So your survival rate at the hospital was 7% higher. And it turns out that wasn't that big of a deal. But the 7%, sometimes 7% is a big deal. And so this next example demonstrates how that can happen. All right, so it's a popular question in hockey. Your turn problem. NHL birthdays. So it has been observed that a large percentage of the players in the National Hockey League are born in the early part of the year, specifically January, February, and March. Get a lot of hockey players born in those 3 months. It has been suggested that this is due to the cutoff dates for youth league participation, and that the older kids excel because at that age group, a half a year difference is a big deal, so they do better at the beginning. They get drafted into higher level teams, more coaching, more ice time. And so they're saying that the system is sort of skewed towards people born in these first few months. And so we want to see just how, if that's true, is there really that many more hockey players born in January, February, and March? So here's the data. In the 2008-2009 season, 159 out of 512 NHL players were born in the first 3 months, January, February, and March. Right? And that represents about 31% of the players. So 31% of the players in the NHL were born in the first 3 months of the year. Now, if everything was even and as expected, you would expect about 25%, because January, February, and March make up about 25% of the days of the year. So you would expect 25% if there's nothing strange going on, and you have 31%. So the difference is about 6%, right? So there's about a 6% difference from what was expected. And what we noticed up here was we had a difference of 7%, right? About a 7% difference. And that was no big deal. Here we have a 6% difference. Do we think that's a big deal? Well, you can't tell just by looking at the percentage, right? So we actually are going to look at the actual numbers of hockey players, right? So we're going to ask, how unusual is this phenomenon? So basically what I want to do is I'm going to go to my normal distribution, and I'm going to approximate my discrete random variable, which is the number of hockey players born in the first 3 months of the year. And what we would expect, the mean is n times p, and n is 159 because we have 159 hockey players. And p, if the 25% is accurate, right, what we expect is n times p, or 128. So we'd expect 128 of the hockey players to be born in those first 3 months. We got 159, right? So what we want to know is what's the probability of getting 159 or more if the mean is 128. So we got our mean, 128. We also need to calculate our standard deviation, square root of n times p times q. Again, they have to add to 1. P and q are always adding to 1. And so the standard deviation is 9.8. So I'm going to convert this 159 to a z-score right here. It's x star minus the mean over the standard deviation. I get 3.16. So this z star right here is 3.16. So the probability that I get 159 or more players born in the first 3 months of the year is approximated by the probability that I get a z-score from the continuous distribution greater than 3.16. And again, the z table gives us these values in here. So to get this value on the right, we have to subtract it from 1. So I have to take 1 minus the probability that z is below 3.16. So let's look up 3.16. See what we get. 3.16. So it's 3.1. So we're in this row. And 0.6. So we're in this column. Hopefully when I expand out, I see I have 0.9992. So we take that back to our problem here. We have 0.9992. That's this area here, 0.9992. But we have to subtract that from 1 to get the area that we want. So 1 minus that is 0.0008. So if you convert that to a percentage, that is 0.08%, or that's less than 1/10%. So how unusual is this phenomenon? It's pretty unusual, because in random samples of size 512, you would expect less than 1% of 0.1% of them to contain 159 or more people born in the first 3 months. So what we're seeing here is something that is very unusual. I guess it could be a result of random variation, but that's an awful small percentage. That's a very extreme value. And so the guess is that some outside influence is probably causing this phenomenon. Right? What it is, we don't know. The whole thing about participation in Youth League, that is, hasn't really been proven. That's just speculation, but it certainly suggests that maybe something is up. Okay, so this is a little preview. Later in the book, we're going to talk about significance. What is significant? So you hear that all the time. That's a significant difference. And the question is, when is a difference actually significant? And what you'll notice is that in this first problem, we had a difference of about 7%. and we concluded that wasn't really a big deal. But in here we have a difference of 6%. And that was actually a big deal, right? That was way far away from the mean. And so how do we define what is significant? It certainly is not just as a matter of percentages, right? Determining significance is a little trickier, and it has to do with these z-scores and areas and probabilities. So we'll explore more of that in Chapter 8. But for now, I think that wraps up Chapter 6.5. So we'll call it a day here, and see you at the summary worksheet. Take care.